Well, I think everything's been said anyway. I mean, you've had a fantastically good number of papers on biomethanization already. What else can I say? Well, I'm going to talk about in-situ biomethanization because actually I think, like Michael, we need to get this working. We need to get this to be a stable and good process because there are all sorts of opportunities, not necessarily in power to gas, but in situations like in rural Africa, where you've got underdeveloped grid systems, you've got lots of sunshine, you can produce electricity very easily, you can use that to put into your digester, if you've got a small digester, community-based, with cheap electrolysers, to produce biomethane, which you can bottle into bottled gas and displace the collection of firewood and other activities like that, and actually do some good to communities if we can get it working. Theoretically, it's quite a simple process. We've heard about the issues about controlling this process. Let's see how we've done at Southampton in solving some of these problems and hopefully passing that information on. But again, most of this you've heard, you know, the conversion of hydrogen to CO2, thermochemical reduction, been known 100 years, biochemical reduction, only first patented in 2007, 10 years ago. And here we are all talking about it now, very enthusiastic about it. So we've come a long way in a fairly short period of time. But why is it taking this long for this concept to become, you know, sort of being talked about? Well, it is energetically inefficient, if you think about it. We've got converting 2 moles of hydrogen, you know, with a big calorific value, to 2 moles of water, and only taking 2 moles of hydrogen into methane. So actually, you know, the energy value of our input is about 14.2 kilowatt hours for the 4 meters cubed we have to put in there to combine with 1 meter cubed of CO2, which only has an energy value of 11.1 kilowatt hours. In other words, only 78% efficiency in that conversion. Well, you'd expect only 50% because you're losing half of your hydrogen, but actually when you combine the hydrogen with the carbon, you get some energy in that bond as well, so you get some of that energy back in the methane bonding. Why is it important to us? Because hydrogen is a hugely voluminous gas, yeah, in terms of its energy per cubic meter, yeah, and it's also very, you know, flammable and very dangerous and very difficult to store. And methane is much denser fuel gas, and much easier to store. And we have also an infrastructure, a distribution system, which can take that to various parts of the world, intercontinentally almost, and allow us to pull out that energy at any point. So, but we also have to take into account energy inefficiencies in electrolysis, but that's getting better. A good electrolyser now may be up to 78 to 80% efficiency, and we can also get some of that extra lost energy back from the heat from that electrolyser, and that technology is improving all of the time. So we heard about power to gas. I'm not going to say much about that. We've heard about the storage and why we want to use methane and not necessarily hydrogen. But we still have to close the energy gap. We can't be throwing energy away in a society like we have at the moment. So we've got to make use of that electrolytical heat. We've got to integrate that into our processes. We can close that gap in biogas to some degree, because if we wish to have biomethane rather than biogas, we have to upgrade that. That upgrading through conventional pressure swing technology, water absorption technology, membrane technology has an energy cost, probably about 1 kilowatt hour per meter cubed of biogas upgraded. So again, we're getting some of that back by doing an in-situ upgrading process. We need to make use of the oxygen which we have, and again, process integration. If we're using this sort of technology in the water industry, where anaerobic digestion is a common process, we also have many aerobic treatment processes in which that oxygen could be utilized. If we're looking at using the methane as a product into gas fermentation through methanotrophs or anything like that, again, they need oxygen in those C1 fermentations. So there's opportunities for integration from our electrolysis process back and gaining some of those value-added materials back into our system. And then in this energy balance, I mean, nobody ever takes into account, but I think it's worth mentioning, yeah, that we actually talk a lot, and we've talked a lot over the last 15, 20 years about carbon capture and storage. That has a huge energy implication in doing that. It doesn't come for nothing, yeah? And actually, if we're starting to actually go from carbon capture utilization, to carbon capture and storage, to carbon capture and utilization, then surely we should be getting some credit back for the energy we're saving in not having to store that carbon. So that should be taken into account when people develop the life cycle models for these systems. So where do we go? Well, we are going to see developments down all paths. It's like a tree, isn't it? People develop new technology. This technology diversifies and people come with different ideas. We got a myriad. And eventually, out of that, all of these ideas come the technologies will break through and will serve the purpose of our society. So we're going to see developments in thermochemical treatment. It's, catalysis and all of these are getting much more efficient, much better, better energy recovery and heat recovery, etc. So we're not going to wipe out thermochemical conversion. But 10 years of development in biochemical conversion, and we've seen some of the results already today in the presentations. We're coming a long way and coming quite fast. But we still don't have any real, defined or market certainty in the technology which will emerge as a winner. Yeah, we've got the in-situ processes we've heard about, where you inject the gaseous hydrogen and CO2 into a reactor. That may be a mixed culture reactor, as we heard from Sandra, or as we heard from Simon, it may be a pure culture reactor. Both are feasible, both are possible, and both are being developed commercially. And then we come to this thing which Michael's been talking about, in situ, where we're trying to use biogas and hydrogen in an existing anaerobic digester. And there we go. So the IB Catalyst project has had an open book. And it's been looking at ex-situ systems, potential for high-rate conversions. But it's also adopted the view, and it's a very strong view, that the in-situ conversion deserves some attention for several reasons. Firstly, we have an existing infrastructure. We have a lot of anaerobic digesters out there in the field, yeah? They're already there, they're already built, they've already been paid for, yeah? They all have good connections to the grid. They're mainly exporting power to the grid from combined heat and power systems, and that process is reversible. Many of our water companies now have into negative power generation in terms of the fee they're being paid, and they're producing electricity for nothing, can't sell it because and again in competition with renewables. Yeah, so they have energy potentially on site which they're generating, which they can use. Yeah, and they can import energy onto site as well through their grid connections, and they have a much bigger interest nowadays in biomethane production rather than CHP because of the incentives have moved. The incentives have moved from power generation being subsidized to renewable heat incentives for good reasons. I came back I've been to China for an IEA mission looking at bioenergy and trying to get China to come on board and produce more bioenergy because what we see now is renewables. China is producing 45% of its power from renewables, from hydro, from wind, from solar. Europe is producing almost 40% of its power from renewables. But when it comes to heat, then we're all doing miserably badly. Maybe Denmark can produce 40% heat from its renewables, but actually when you go to China, it's 5%. Yeah, and that's why they're still burning coal. They're still got to produce heat, and we've got to actually start to think about power to storable and burnable fuels or platforms for production of chemicals from them. And methane is a hugely good starting point for C1 fermentations. So in-situ potentially offers a one-stop shop for biogas upgrading while also increasing the potential methane yield per tonne of carbon arriving at the plant. And that goes for all of these bioenergy plants from energy crops you're producing so much carbon per hectare of land. Yeah, that's what photosynthesis does. It fixes that carbon. You're taking that carbon in the form of maize, you're putting it into a digester, and you're losing 50% of it as carbon dioxide. Yeah. If you can put some photovoltaic panels in your field, or some windmills in your field, then you can make all of that carbon, which has been fixed by the sun, by those plants, as Mike Mason was saying, this is the way forward, photosynthesis. Then you're capturing that carbon in a more efficient way by helping photosynthesis, by producing that extra hydrogen to get rid of the oxygen. Yeah, and that's what it's all about. It's getting rid of oxygen, basically. We can retrofit digesters relatively economically, so it's quite competitive, low capital costs and fairly low operating costs. So all good things. But what are our limitations? Well, we've heard from Michael Cheshire. The limitations are in the in-situ process. The amount of carbon you have to convert depends upon the organic load you're putting in there. In other words, the amount of materials, input materials, be it maize, be it sewage sludge, be it food waste, which is going in there, and that is limited by the process organic loading rate which your digester can cope with. And that really depends upon the volatile solids content, it depends upon the degradability, it depends upon the hydraulic retention time, but typically we feed an anaerobic digester at somewhere between 2 to 4 kilograms of VS per meter cube per day. Maybe a bit higher if you're pushing it, but it may be a slightly less efficient process. So we wanted to look at this, so we started to run phase 1, if you like, a traditional AD with no hydrogen input, purely and simply to establish a baseline condition of which we can monitor and effectively give some performance indication on our plant. Phase 2, we decided to inject hydrogen to convert internal CO2, which had been produced in that digester, to enrich the hydrogenotrophic population and to try and produce an enriched biomethane output up to 100% if we could, but let's not be too optimistic at the moment. Michael wants 80%. Sandra said 80%. What can we really get? But we are ambitious and we said, well, actually, let's try and overcome this limitation because, we can develop a whole new ecosystem in this existing anaerobic digester. Our organic load is primarily being converted by acetoclastic methanogens producing hydrogen. But what's stopping, a second trophic level of hydrogenotrophic methanogens establishing there? They've got a different feedstock. They might not be limited by the same conditions. So can we put in exogenous CO2 into this digester and stimulate a higher level of hydrogenotrophic methanogenesis, and in fact use the anaerobic digester as an in-situ and an ex-situ process? Yeah? And if we can do that, we might only need to upgrade one anaerobic digester and feed the biogas from several anaerobic digesters into it. And then we've got a real economy in terms of our CapEx and OpEx. So that was the plan. So here we go. Here's our baseline, 100 days. We never do things fast at Southampton. I used to blame it on the fact that I never had time to see my students, so they'd be hanging around for 100 days waiting for my next piece of advice. But now I've retired, that can no longer be the case. So 100 days, and you can see a fairly good methane percentage in at about 54%. CHP production in terms of specific methane production, fairly level at about 0.8, 0.9 litres of methane per litre of reactor per day. That's volumetric production, not the specific. Talking to my scriptwriter down there. So now we thought we'll take it easy, and everybody said, oh, it's a big problem, it's a big problem. So we said, let's go gentle, and let's be stoichiometric. Let's just put in the hydrogen at the rate at which we can utilize it in relation to the CO2. So we only added until we actually found no hydrogen left in the headspace gas. So it takes quite a long time. We put in 10%, 20%, 30%, oh, we got a bit brave, we got to 50, oh, it's doing well, 75, 100%, Well, 100% stoichiometric conversion, and our methane concentration up here is at 95%. So, yeah, if you take it slow, and if you do it stoichiometrically, you can do it, yeah? And okay, we operate with small reactors in a very careful way, etc., 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 etc. But you do see some blips in here, boom, boom, when we go to 100%, and we'll explain those in a minute. So gradual hydrogen injection, methane content going from 50 to 95%, volumetric methane production going from 0.86 and doubling that to about 1.51. So we've doubled our volumetric methane production. We've utilised all of our carbon going into that system. I'm not looking at what you're pointing at me. Well, so here we go. So now we're going to take exogenous CO2. In other words, we're going to take methane, biogas from other digesters and put it in there. It's up to 125% of the carbon load, 150% of the carbon load, 200, 250, 275, 300%. Yeah? So we're now taking the biogas from two other digesters and putting them into this digester, and we are still achieving, with some blips as we keep increasing the load, but you know, one reactor is fairly constant, and we're still getting our 95% biomethane conversion. So we're quite happy with that. And those experiments are over a year, so they've got a long track record, etc. Yeah. So all our external CO2 converted, 95%, and now we've gone up to 2.76, 3 times, or more than 3 times, the volumetric productivity. James, our hero, and Anna do all the microbiology for us, but you can see the methanogens, the archaea, are still a fairly small part of what's in that digester. Yeah? Most of it is just bacteria. Yeah? But as we step up, you know, phase 2 and phase 3, phase 2, phase 3, the archaea population is increasing, yeah? And it's also changing. And I won't explain all that, ask James. But also the synthetic acetate oxidizers, the population is increasing as well. So we're changing our microbiology. We are getting that extra trophic level in there of organisms in that digester. So there's our now flow chart. A couple of anaerobic digesters feeding the single anaerobic digester sludge going into all 3 of them, but the biogas being fed into those and being upgraded to biomethane. So not a bad system, and one which makes very good use of things. So the bottlenecks is the pH. I showed you that blip. We got to 95%. Look what happened to the pH when we got to there. As Richard said, it becomes unstable. You know? And the pH shoots up mainly because you've got no carbonate left. You've used it all. You convert it all to methane. So you've got no acid. Yeah. So your pH, your alkali goes up. But providing you control it, we just brought it back down to 95%, and we started to look at this relationship between the carbonate in the headspace and the pH, and you can see as the amount of carbonate gets lost, the partial pressure of CO2 goes down, then your pH goes out of control fairly rapidly. But if you start to understand that relationship, and it does fit a curve, it does fit a logarithmic relationship, and you can put out in your constants for the equation to describe that, then you can start to understand the basis of a control system for this based on measuring CO2 partial pressures in your headspace. And there's our blip. But we were working at a tan of 1.5. What happens if you increase the tan? Well, we did increase the tan, and again a long baseline, and then a fairly rapid step up in injection of CO2 and hydrogen, and again we're reaching stability, and we're reaching a fairly good methane percentage of 95%, with tans of 3 and tans of 4 milligrams per litre, quite high ammonia. So alkalinities, alkali is there already, alkalinity. And we wanted to stop addition and start addition to see how quickly we could actually change things and how quickly things could acclimate. And we're quite happy with the response, to be perfectly honest with you, to these systems. We wanted to look at rapid methods to actually develop this model further so that we could have a good control system. My eyes are closed. So we've developed a rapid system which we bubble biogas through different sludges of different types and actually start to simulate these different curves, and we find these curves of all of the same type. And we also thought, well, let's do it with a food waste digester, which we know has got a very high TAN, TAN of about 5. Can we really inject hydrogen into a food waste digester? And yes, we can. Here we are. We're injecting it, and the pH goes right up, of course, and it gets quite bumpy at the top, but we're still producing biomethane out of that food waste digester over fairly long periods of time, another 260 days. What patient researchers I have. And again, the curve, the pH curve, follows the same equation. Yeah. So we do have a method now of determining rapidly what will happen with different types of substrates, different types of digestate, and to start to formulate a decent control system based on partial pressure of CO2 using infrared sort of technology to bring these processes under control and to allow us to achieve fairly high levels of biomethanization within there. So outcomes, we can convert normal digesters to biomethanization quite quickly. We can expect to get about 95% methane. It's our maximum safe level, we think. We wouldn't like to go higher than that for in-situ conversion. With the food waste digester, we only get about 90 because then we start to tip the pH, because it's got a very high natural pH anyway. In there, it's about 7.9. Yeah? We think that we start to inhibit or kill the hydrogenotrophic methanogens, or the precursors for the biomethane, at about pH 8.4, 8.5 is our estimation. And we can provide stable operation through maintaining partial pressure of CO2, and our rapid method does allow us to do something. I want to talk, I am going to go over time because I think this is important. Yeah, because we're talking now, and research councils are talking, Europe's talking about carbon utilisation. Yeah, we've gone from carbon capture, now we have to use carbon utilisation. Yeah. And what we're doing, in a biogas plant, an anaerobic digestion plant, we've got CO2 production of 2 to 20 tons per day. Yeah, it's very little. Yeah, we can do that quite happily. But once we move to an incinerator, we're producing 200 tons of CO2 per day. We go to a cement kiln, we're 5,000 tons per day. We go to a power plant, and we're 50,000 tons of CO2 per day. Yeah? So we're talking orders of magnitude difference. Yeah? And that's on a log scale, that graph. So the amount of CO2 which we're producing. Yeah? And what are we doing? We're doing conventional reactors producing 4 meters cubed of methane per meter cubed per day for a municipal wastewater treatment plant. We'll require a upgrading facility, an ex-situ biogas situation of about 2,500 meters cubed. But for a cement kiln, we'd need 6,360 meters cubed of reactor. Unrealistic, yeah? What would we need for a power plant, yeah? I invited Simon because his group is producing probably the highest rates of conversion we've seen in the literature, and I'm quoting there 950 millimoles per litre per hour, which is low compared to what he's just told us, about 500 meters cubed of methane per day. So if we can convert even at 400 litres per litre per day, a cement kiln would require a fairly big tank, 6,000 meters cubed, and a power plant would still require 10 reactors of that size, yeah? So we've got to move up. We've got to start achieving those rates which Simon was talking about if we're going to go to carbon utilisation. And remember, we've got to produce for each meter cubed of carbon dioxide we're converting, we've got to produce 4 meters cubed of hydrogen. And that's a huge energy input. Yeah? And don't forget, we all talk about producing our chemicals, our bulk chemicals from it, but actually, if we took all of the fixed carbon outputs, which we produce currently, yeah, we'd only need 5% of them to produce all of the chemicals which we currently produce from fossil fuel sources. I'll give you an example. We currently use 75 million tons of methanol, yeah? Methanol is produced from natural gas, from methane, yeah? 75 million tons of methanol produced by biomethanisation would take the CO2 output from 7 power stations, and that's the world consumption. Yeah. So let's get real. We're not really going to go to carbon utilisation. If we are, we've got to remember that the main agenda must be reducing fossil fuel usage in power production. We must concentrate our biomethanisation processes, our carbon utilisation processes, on those industrial processes which create CO2, not as a necessity. Like a cement kiln, to produce cement has to produce CO2 because it has to use lime and limestone. So I think that's my final message for this conference. We have to look at all of these things in a context. And thank everybody for listening. And very sorry to have gone over time. My privilege. And now I have to close this conference down after I've answered any question. One question I'm allowed.
Talking about having an easy role as a chair. Any questions for Charles? Yeah. Okay.
Mike Mason.
You talked about co-locating with a cement plant or a power station and these sorts of synergistic opportunities. Don't forget, if you are producing massive amounts of hydrogen, you can use the oxygen for oxy-combustion and thereby reduce a vast amount of the energy required for carbon capture and storage.
Yeah.
And I think what we're looking at is the co-location of these things. And they make so much more sense if you can put large scale next to power stations.
Yeah, I mean, I agree, mate. There's multiple solutions for all of these things, but we have to get the scale right, I think, we are moving towards everybody talking about carbon utilisation, but we've got to get the actual realism of that out there, yeah? That, even if we produce every chemical we use at the moment, it's only going to use 5% of our carbon output at the moment. We've still got to reduce CO2 emissions from fossil sources.